All right, we're on to another video for section 9.3. We're going to take a look at a few more examples here. And in particular, we're looking at examples where we have a little bit different thing that we're taking a square root of. In our previous examples, we would end up with x squared, and then we would take the square root of it. But this time, instead, we have x minus 1 squared equals 25. And we want to see how we can solve this. Well, let's get at it. And when you have something inside our parentheses that's still taken to the second power, as long as we just have this one x sitting here, we can actually just begin by taking the square root. And this is something which is tremendously helpful and imbues a significant amount of additional utility of our vertex form, if you remember that, because we can simply just start and take the square root of both sides. The square root of x minus 1 squared is just x minus 1, which is pretty nice. But we have to think about this plus or minus the square root of 25. And you think, well, what are the numbers that multiply to make 25? Well, the only factors are 5 and 5. And since we have a pair of them, we get to pull them out. Or if you just remember from your multiplication table, the square root of 25 is 5. So we have x minus 1 is equal to plus or minus 5. So I'm going to proceed like I did before, and I'm going to get x alone, because that's how we solve for x. So I'm adding 1 to both sides. We have x equals 1 plus or minus 5. And you might be tempted to say, well, those are our two solutions, we're done. But we can simplify this and make it clear what the actual numbers are. And that will be done by separating plus or minus 5 into two separate statements, which are x equals 1 plus 5 and x equals 1 minus 5. 1 plus 5 is, of course, 6. So we have x equals 6 as a solution. And then 1 minus 5 is a negative 4, which gives us x equals negative 4. Those are our two solutions. So we have two solutions. As I said, that's the conventional case. We have two solutions here. And if we think about why this works for a moment, because you might say, but we took the square root of 25. How do we have 6 and negative 4? Neither of them are 5. If we were to plug 6 back in, 6 minus 1 is what? 5. 5 squared equals 25. So 6 is going to give us the original statement. It will make it true. Likewise, negative 4. Negative 4 minus 1. Negative 4 minus 1, two minuses. They add together like normal, except our solution is negative. So negative 4 minus 1 is negative 5. Once again, negative 5 squared, negative 5 times negative 5 is positive 25. So both of them, in fact, work. If we look at number 9, it's exactly the same song and dance. We begin by taking the square root of both sides. That leaves us x minus 3 on the left side. On the right side, we have plus or minus the square root of 16. Now, if we think about this for a moment, 16 is 4 times 4. We can pull the 4 out. So the square root of 16 is simply 4. So we have x minus 3 equals plus or minus 4. Then we add 3 to both sides. We have x equals 3 plus or minus 4. We separate it into two separate statements once again. So we have x is equal to 3 plus 4, and also x is equal to 3 minus 4. 3 plus 4 is 7, and 3 minus 4 is negative 1. Those are our two solutions, x equals 7, x equals negative 1. Once again, we have two solutions. Again, the steps are not anything too crazy. You see that square root sitting all by itself on one side, and you only have the one x somewhere, like we have in these examples. You just take the square root and then deal with the consequences of it in the subsequent steps. So being able to take the square root of both sides is something which is extremely powerful in solving quadratics, and it saves us from needing to go through and try to factor this stuff. Because otherwise, we would have to subtract 16 to the other side, distribute this through, factor it. The whole thing would be a big, ugly mess. Instead, we can just take the square root. And I, for one, would like to make my life in mathematics as easy as possible. And hopefully that's the case for you too. But we're about to take a look at another, what I would say is probably a little bit more challenging example. Example 10 here. we have 4 times quantity x minus 3 squared is equal to 9. Things are going to get a little bit funny here. So we can see the original problems. Now, the problem here is that we actually can't really just immediately take the square roots of both sides. Technically, you could, but I think that would be more confusing than is really worth it. So what we need to do is we need to get our x minus 3 squared alone. That is sort of that's basically our x term right now. It's the whole thing. We're going to get our squared term by itself. And we're going to do that by dividing by our 9. Because this is ultimately the best option we're going to have in terms of solving this without being too overly confusing. So we're going to divide by our 4 to get our x minus 3 squared alone. And unfortunately, 9 divided by 4 can't really be simplified in any other respect because 4 does not go evenly into 9. And having a mixed number here will really set you back a large distance, as will having a decimal, because it'll be much easier for us to take the square root of both sides if we leave this as a fraction. So just like before, we're just taking the square root of both sides again. So on our left side, we're just left with x minus 3, which is pretty nice. And our right side, we now have plus or minus the square root of 9 divided by 4. And you might be thinking, oh crap, how do I take the square root of a fraction? Well, square roots have an exceedingly useful feature, which is that we can actually say this as being, well, this is actually just the square root of 9 divided by the square root of 4. I should say plus or minus the square root of 9 divided by the square root of 4. And then you can treat each piece individually. And why this is so useful is if you think about it, well, the square root of 9 is the number that you multiply 9 by itself to make 9, which is 3. Likewise, the square root of 4 is 2. So the square root of 9/4 is 3 halves. And if you needed to check it real quick, you could say, okay, 3 halves times 3 halves, top times top, bottom by times bottom, 9/4. 3 times 3 and 2 times 2. So 3/2 is in fact the square root of 9/4. And then once again, we need to proceed with this problem as we did before. So we have x minus 3 equals plus or minus 3/2. We add 3 to both sides. Let's move this up a little bit. That gives us x equals 3 plus or minus 3/2. And now we have to remember how to add fractions to whole numbers. And this is going to require us to split this up once again. So we have x equals 3 plus 3/2, and x equals 3 minus 3/2. Well, in order to add fractions together, we of course need to have the same denominator, number on the bottom. And I know that 6/2 equals 3, because 6 divided by 2 is 3. And 6 plus 6 is going to give us 9. So we have 9/2. Likewise, down here, we have 6/2 minus 3/2, which gives us 6 minus 3 is 3 divided by 2. Now, that problem may have been a little bit unnecessarily difficult just from needing to add and subtract fractions. Perhaps if I had been really nice, we would have had x minus 1/2 inside our parentheses. However, it still does an excellent job of illustrating what is going on in this problem. We can still take the square root of both sides, but we need to make sure our squared term is by itself. That was our first step when we divided by 4. And then when you take the square root of a fraction, you simply need to take the square root of the top and then take the square root of the bottom individually to figure out what our fraction is going to end up being. And I also made sure to check and demonstrate that that was in fact the case. From there, it's simply a matter of following the regular steps and utilizing the properties of fractions in order to get to your solutions of, in this case, 9 halves and 3 halves. And if you'd like to double check that those work, I recommend that you do that by plugging them into the original equation on your calculator on your own time. Now you can go ahead and do a few examples exploring these additional options that have been presented in this video.